carry on. Who went out that way? Did anyone find a coffee machine?
Yeah.
Yeah, there was one.
There's a vending machine.
It's a vending machine. Okay. Good. So that was not mine. Then, all right. So we'll carry on. Let me talk about section 1.2. Section 1.1 in the book is worth reading, and it just lists off a whole bunch of different scenarios, situations where we will learn how statistics applies in this in such and such scenario. It's interesting. If you want to skim over it, you can. But I thought it was good. Section 1.2. And I know I'm going a little bit out of order just through the sections here. Talks about the difference between an experiment and an observational study. So in statistics we say your data will generally come from either an experiment or an observational study. We talked about surveying methods and sampling methods. In those cases, when you're selecting a sample, you will then perform either an experiment or an observational study on the people you have sampled. Okay? Most likely an observational study, but could also be an experiment. The data you get will, either be generated from an experiment or an observational study. This is in contrast to what we might call anecdotal data, okay, where people say, well, this happened to my grandmother, and so this is what I think, you know. And so, you know, they might, someone might say, my grandmother got this procedure and it worked, or it didn't work, My friend suddenly changed their diet and ate this and that, ate rocks and whatever, or, whatever they did, and it worked for that person, okay? So does that constitute evidence for something? Maybe that's anecdotal evidence, but in terms of statistics, we don't deal with that. Okay, we say, well, that's nice, but in terms of applying math and making conclusions from limited data, anecdotal evidence, we don't use. Okay, so we're talking about experiments, observational studies, and we have rules and things about these things. Okay, so in an experiment, what we do we interfere. I'm having trouble spelling things today. We interfere with our subjects. And specifically, what we are doing is we assign treatments to our subjects. Treatments are a set of conditions, okay? So to our subjects, we assign treatments to them. We don't let the subjects choose which set of conditions they get. We say, you are getting this set of conditions, okay? And ideally, we can control as many aspects about our subjects as possible. And what we would do is we would make, let's say we have two groups of subjects. We have a control group and a treatment group. Okay? Ideally, everything about both of these two groups are as identical as possible, except for one thing, and that is the thing that we're interested in. Okay? So maybe we want to know, does, I don't know, just half an hour of physical activity every day, does that, will that lower your blood pressure over a 30-day period? Okay, well, half an hour of physical activity every day for 30 days, lower your blood pressure. Okay. Well, that would actually be a very difficult experiment to carry out, but what we would do is we would have to ideally we would control the two groups as identical as possible. They would have, both groups would, everybody would eat the same diet, everybody would have, the same schedule and activities and everything, with the exception that one group does half an hour of physical activity and the other group does not. Okay? And that way, at the end of the study, if we do observe a difference in blood pressure between the two groups, we can say this difference in blood pressure is because of the one difference, which is that this group did exercise and this group did not. Okay? If we didn't control all of these different things, then there could be a lot of unknown questions. Okay? If we just, in the different groups, let's say this group ate, fast food every day, and this group ate vegetables every day only, or something, and then we observe a difference in blood pressure, we won't know if the difference in blood pressure is because of the exercise or because of the diet differences. Okay? So ideally, in an experiment, we can control as many aspects as possible, with the exception of, one factor, and that's the one that we're interested in. Okay? Control as many aspects as possible. So all subjects have nearly identical conditions with the exception of the one factor of interest. Obviously, it's much easier to do this kind of thing with plants and animals than it is with people, because people have feelings and rights, and so some experiments, because of this aspect of control, are simply not possible to do on people. Okay? If we wanted to know if the effects of methamphetamines on the brain, a true experiment would say, well, thank you for volunteering for our experiment. Half of you are going to start using methamphetamine starting tomorrow every day. The other half of you, you will stay away from them, and then we're going to see what happens to everybody at the end of the experiment. We would probably learn a good amount from that experiment, but that would be unethical, and we would not be able to do that. Okay? So,
do you really want the subjects to not have nearly identical conditions?
oh, did I say that? So all subjects have nearly identical
With the
conditions.
exception of one factor. So if you're measuring blood pressure change, would you want them all to possibly have high blood pressure, or would you want them to have different blood pressures?
So that makes the answer to that is a little more complicated than I want to get into. Basically, you would be measuring the change in blood pressure from the beginning of the experiment to the end of the experiment. So, yeah, you would assign the treatments randomly, and hopefully that would make the two groups as identical as possible. Although, I guess you can manually control for that also. But that changes things. But anyway, big picture idea is you want everybody to have almost identical conditions, except this group is under one slightly different thing than this one, and that way at the end of the experiment, if you see a difference in whatever you're trying to measure, you can attribute that difference to that one difference between the groups. Okay? And so, at the end of the experiment, if your two groups being the control group versus the treatment group, if the two groups have a difference you can attribute the difference to the difference in treatments. To the difference in the set of conditions. Okay. So you can make a cause and effect conclusion. Okay, assuming your data supports that. So that's experiments. As you read your textbook, it'll mention some topics such as blinding and placebos and stuff like that, which is good to know. Observational studies, on the other hand,
Wait, does the difference have to be a change in the treatment group, or can it be either one? Like, what if the control group actually showed a rise in blood pressure?
Yeah.
Or lowered blood pressure from not working out? Would that work too?
yeah, just at the end of the day, when you're comparing one to the other,
As long as they're different, it doesn't
if
matter.
they're different, you can say that difference is because the
Okay.
set of conditions that we imposed on them were different.
Okay.
Okay? And really, when we say the set of conditions are different, it's really all the conditions were the same except for this one thing. Okay? So you can then say it's this one thing that's causing this difference, assuming your data supports it. So that's the idea from an experiment. On the other hand, if you can't do an experiment for ethical or practical reasons, then you have to do an observational study. Observational study is still valuable and useful. It's just that you cannot make the cause and effect conclusions. Okay? So observational study, we do not interfere with the subjects other than taking measurements, okay? And then at the end of the observational study, if you do observe a difference between different groups, let's say you observe a difference between those who exercise and those who don't exercise, we cannot make a cause and effect conclusion. We cannot say that exercise is the thing that makes a difference, okay? Because, you know, when it comes to blood pressure, when it comes to anything that you're measuring, there could be a whole bunch of different things that influence it. And we didn't really control anything else other than, well, we didn't control anything other than making observations. And so we could say exercise is associated, but it's not necessarily causing it. Okay. Silly example is if we did a study on the type of car a family owns, or maybe the value of a car that a family owns versus performance in school, what we will find is that families that have expensive cars generally have kids that perform better in school than families that have cheap cars, okay? Does that mean the solution to help your student do better in school would be to get an expensive car?
Yes.
We would like so, right? But we know that's not the case, okay? And the answer to, you know, why are the families with expensive cars, why do their kids generally perform better in school than families with cheap cars? Well, the answer is very complicated and unknown, okay? And, you know, we assume it has to do with socioeconomic status, but socioeconomic status in of itself doesn't explain why school performance is different. It's just something that we kind of just say, oh, well, there's a difference in social classes and that explains everything, but it doesn't, you know? So, life is complicated. There's a lot of things that influence what happens. But the results of an observational study can point us in the right direction to finding these answers. Although you know, we're always limited in what we can say. Okay, that's that on observational studies versus experiments. We'll leave it to you and your reading to get into a little bit more depth there. And how am I doing on time? 45 minutes. All right. Okay, so we're going to jump into chapter 2, and I'm going to cover a bunch of stuff. I'm probably not going to cover everything, and I think the topics in chapter 2 are introductory and easy enough for you to read the book and solve a lot of these problems on your own. I've provided, I've made a video on how to find the standard deviation, and I posted that online already. We'll talk about that in a bit. But again, if you have any issues or things, post your questions on Facebook, or you can come during office hours. You know, as the topics go on and get more difficult, I'll try to spend more time on them. But I think chapter 2 is intro enough that we can go quickly. All right, so chapter 2 is all about data. And imagine we are gathering data, okay? Imagine I say, let's go around the classroom, and from every student I want to know your gender, your height, your weight, your age, your hair color. Okay, let's say that we're going to do this. Okay, we're not actually going to do this, but let's just say this is we're going to do your student info. Okay, and so we're going to find out gender, height, weight, age, hair color. How would we organize our data? If we go around gathering this data, how should this be organized? How would you set this up? gather your data?
An Excel file.
Okay, yes, great. An Excel file, that's a great place to start, okay? Because what we're saying is we're going to have a table of data, okay? And what would we set up in our Excel file? We'd have column headings, right? And if we wanted to, maybe we'd put in a name column. This maybe we would or we would not, or just a number, okay? And then we would have the different column headings. We'd have gender, height, weight, age, and hair color. Okay, so each row represents a person. Okay, so each row is a subject. And is a person, okay? At least in this class. And each column is a variable. Okay? Variables vary from student to student. Okay? So it's a variable. We have two types of variables that we will concern ourselves with. We have numeric or quantitative variables. And numeric variables tell us how much or how many. And then we have categorical variables. And they tell us what type or what kind. Okay, so this is simple enough, but let's just let's go through the different variables that we have. Gender would be numeric or categorical? Categorical. Height would be numeric, telling us how many inches tall we are. Your weight? Numeric. Age? Numeric, how many years old you are, and hair color? Categorical. Good. Okay. The book goes into further detail about continuous versus discrete numeric variables. Okay, so technically all of these are continuous, although the age we generally report in discrete terms. But how old you are is actually going to be something like 25.447 years. But we generally just report as full numbers. A true discrete numeric variable would be how many siblings do you have? Okay. So this would be numeric. Okay. You either have 0, 1, or 2, and your answer can only be a whole number. Okay, you cannot have 1.5 siblings, okay? I mean, we have things as half-brothers and half-sisters if they have the same, you know, one parent is common but the other parent is not. But we either say they are our sibling or are not. We have to give some kind of answer here, okay? So you cannot have 1.6 siblings, although the average number of siblings could be 1.6. Okay, so do I need to write that on the board? No. Okay. You'll read it in the book. There's continuous, discrete. General rule of thumb, although this is not the exact answer, continuous means a decimal answer is acceptable, and discrete, generally a decimal answer is not acceptable, although that may not be the best way to put it, because maybe like shoe sizes are discrete, although you have half sizes there. Okay. Okay, and so quick question. Let's say I put in your zip code. I said, what is your zip code? Is that numeric or categorical? Categorical, okay? Zip code, even though the answer is a number, it does not tell us how much or how many, okay? It does not make sense to make comparison statements about zip code. It doesn't make sense to say, oh, your zip code is 91005 and your zip code is 91334, therefore you have 332 more zip code than this guy, okay? It doesn't make sense to make those kinds of statements about that. So zip code would be categorical. As you, when you read a problem, okay, it may not be as obvious as this, okay? But you have to think about, if I were to gather this data, when we gathered the data, what did the column look like? That would guide you into answering whether it's numeric or categorical, okay? So let's say I made a statement. Okay. Let's say we surveyed 100 people, and we asked whether they own a cat or not, and we asked whether they own a dog or not. 35 said they owned a cat, 38 said they owned a dog, and 52 said they do not own a pet. Is this, how many variables do I have? And are they numeric or categorical? I said, we asked 100 people. Do you have a cat or no? Do you have a dog? And then, I don't know what numbers I said. 34 have a cat. We'll say 39 have a dog. 55, no pets. Okay, how many variables do I have?
3.
Okay, so just think about, if you're going to set up a table to gather your data, how would you set your table up? How many columns do you need?
3.
Okay, what are those column names? Yeah, redundant information in your table, okay? A database analyst would say, this is terrible. How many columns do you really need? 2. Do you have a cat? Do you have a dog? Do you have neither pet? If you answered no to the cat and no to the dog, that means you don't have a pet, right?
No.
Oh, okay, sorry, okay. Neither cat nor dog, I should say this. Okay, no cat or dog. No cat nor dog. Okay, sorry. Because these are the only questions we ask. Do you have a cat, do you have a dog? Okay? 55 said neither, okay? So, cat, dog, alright, and then whatever. So, you only need 2 columns, okay? And both of those columns will be answered with yes or no. Okay? So we have 2 variables and they're both categorical. Okay? So if you think about this, cat, dog, and you're either going to have yes, no, 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 or yes, yes, or whatever. Etc., etc., etc. Okay? So you have 2 variables. Both are categorical. We want to create summaries of our thing, okay? So when I say 34 have a cat, 39 have a dog, I am summarizing the results of this table the table actually has 100 rows, right? 1 for every single person. I'm summarizing it just into 2 rows. So we have something called a frequency table. Okay? And the answer is, do you have a cat? And people either answered yes or no And if we have a total of 100 people, and I look at the count, my summary would be 34 and 66. Say no. Okay. This is a summary table for do you own a cat or not? Okay. We can turn this into a bar chart. And we would have a column for yes and a column for no. Vertical axis indicating how many? 10, 20, 30, 40, 50, 60, 70. And I would have a bar for yes that goes up to here, and a bar for no that goes there. Okay. What kind of data do I have here? What type of variable do I have? Categorical data. Not a trick question here, okay? We asked, do you have a cat? And the answer to that question is yes or no, okay? I am having a count. We said how many people had said yes and how many people said no. But these are summaries. The underlying variable is answered with a yes or no, so it's a categorical variable, okay? So don't categorical variable. So don't confuse yourself. This is a categorical variable, and it can be summarized with a frequency table or a bar chart. Creation of the bar chart, okay? One thing you'll notice about the bar chart is that if somebody came along and decided to put the no column on the left and the yes column on the right, in terms of the bar chart, and made something that looks like this, is that allowed? Can you put no over here and yes over here? Yes. This is perfectly valid, okay? You can change the orders of the bar in a bar chart and still be okay. You can change them into increasing order, decreasing order, alphabetical order, whatever order you want. That is fine, okay? Order of the bars doesn't matter. On the other hand, we have numeric data. Okay. So let's say we asked a bunch of students, how many siblings do you have? Okay. And you know, we asked a whole bunch of different students. I'm not going to number them, okay? And let's say their answers were, you know, the first student I asked had 0 siblings, and then this person had 2, and this person had 1, and another person had 1, and this person had 2, and this person had 1, and this person had 0, and this person had 3, and this person had 5. Okay? Let's say these were the answers, okay? I have, this would be the raw data of people, and we can summarize this, okay? With another frequency table. Okay? And this would be how many siblings and then this would be the count of people with that many siblings. Okay, we would just write frequency, okay, but that's what that represents. So the answers, we have 0, 1, 2, 3, 4, 5, and we'll just stop there. How many people had 0 siblings? 2. How many people had 1 sibling? 3. How many people had 2 siblings? 2. How many people had 3 siblings? 1. How many people had 4? And how many people had 5? 1. Okay, so this is what our frequency table would look like here. Okay. In general, you would just, this is a numeric variable, and although I put this, it would just generally be the variable name on this side and the frequency table, or frequency on that side. Is the creation of this frequency summary table okay? And we could turn this not into a bar chart, but we call it a histogram. Okay. And we start off at 0, and we go to 1, 2, 3, 4, 5, like so. And the height would be 1, 2, 3, 4, 5. And I would make bars. So for the bar starting at 0, I would make 2 units high. The bar at 1, I would make 3 units high. The bar at 2, I would make 2 units high. 3, I would make 1 unit high. 4 is 0, and 5 has 1 unit. This is a histogram. Histogram, you'll notice, does not have spaces between the bars. And could we rearrange the bars if we wanted to? No, because the order of the bars is determined by the number line. It goes 0, 1, 2, 3, 4, 5. You cannot change the order of numbers. And what kind of data, or what kind of variable do we have here? This is a numeric variable. Okay, so for a numeric variable, we have frequency tables, but when we represent them graphically, we call it a histogram. In the book will also talk about dot plots, which are similar to histograms, except you use dots rather than bars. And then they'll also make histograms with different bin widths, okay? Histograms with different bin widths, conceptually the same, except that maybe we are including a range of values for each bar. So let's say we didn't ask you what your weight was. My voice suddenly got all weird. Let's say we had you step on a scale, okay, and then we recorded your weight. Okay, and let's say nobody had a problem with this. We do this, okay, and so we would get a wide variety of weights, okay? Now, if we made a frequency table, do you think we'll have, let's say we had a digital scale, do you think we would have a whole bunch of people with the exact same weight? Probably not. We might have somebody who weighs 133.6 pounds, and we might have somebody who weighs 133.2 pounds, and there might even be a few people, like 2 people who weigh the exact same weight, but most likely you're not going to have very many people weighing the exact same weight. So if you made a frequency table of each individual value, you're going to just have a whole bunch of different weights listed, and every frequency will just be 1. Okay? That's not going to be a very useful table or efficient table. So what you would do is you would create a table that says, how many people do we have between 120 pounds and 129.9 pounds? How many people do we have between 130 pounds and 139.9 pounds? And you would set up what we call bins, that way, and then you'd say, oh, I have 2 people in the 120s, and I've got 3 people in the 130s, and I've got 6 people in the 140s, etc., etc., etc. You would then create your histogram that way, or I mean, you create your frequency table that way, and you would use that to make your histogram. Okay? This is illustrated in the book, I think, quite clearly, and I hope my explanation here makes sense. If you have questions, don't hesitate to ask. Yes?
I don't understand how that histogram makes sense because, you know, I mean, it's going from 0 to 1, 1 to 2, right? I mean, so...
Okay, so you are thinking the bars should be centered at the number. Is that what you're...
Yeah.
Okay. Yeah, that might make sense for a discrete variable, but the idea is when you draw bars like this, the general thing is that where the bar begins, it's how many are between 1, where this number begins, and up to, but not including the boundary over here. Okay?
What
So,
about in between? I mean, like between 1 and 2. I mean, I guess...
so you would nobody would have 1.6 siblings. Okay? So essentially when you have a bar that starts at 1 and goes up to 2, it just counts 1, okay? If it was a continuous variable like how many, I don't know, something else, not how many, but something, okay? It would be technically from 1 to, when it ends here, it goes 1.999, okay? And then this bar that starts at 2 goes from 2 to 2.999, okay? Yes?
I see what he's saying, because it kind of looks like, if you look at the 2, even like the line directly above it, looks like
Yeah,
it's going up.
I know what you guys are saying, and I'm telling you that this is how the people who decided how histograms should be drawn decided how histograms should be drawn, and so that this bar that starts at 1 says all the numbers including 1 and going up to but not including the right boundary. Okay? So in this case means how many people have between 1 and 1.999 siblings, and because it's a discrete variable, that just basically means how many people have 1 sibling. Okay? If, let's say I change this to this, okay? And we're talking about how much does your pet weigh, okay? The weight of your pet is a continuous variable, okay? So maybe you have a cat and it weighs 8.76 pounds, okay? So this bar then says how many people have pets that weigh between 0 and up to 9.999 pounds. How many people have pets that weigh between 10 and 19.999 pounds? Okay, that's what these bars mean, okay? I know it feels a little odd when there's only one number involved, but that's how they decided these things should be drawn, and I'm not going to try to change it just because it feels weird. All right? Yes, question in the back.
For the y-axis, could you report that in percentages?
You could.
So that would benefit or...
I guess it depends. Percentages generally are more applicable to bar charts. Okay, so if you want to change this to a percentage, that's fine. Not generally the case for histograms. Okay? I'm going to run out of time here. Okay, so just imagine we've drawn a whole bunch of histograms. Okay, we looked at things like people's heights. Okay, so let's say we asked all the women in the classroom, you know, how tall are you? And we made a histogram, and it looks like this. Okay, actually, our classroom histogram would not look like this. Let's say we asked, you know, 1,000 people, 1,000 women, how tall are you? Then the histogram might look something like this. Okay. What does this histogram mean? It means people who are in the middle, average height. These heights are most common. Are there people who are taller than average? Yes, but those heights are less common. Are there people who are shorter than average? Yes, but those heights are also less common. And the further we get away from the middle, or what's considered average, the further we get away, the less common it becomes. Right? I don't know if I did that too quickly. We can summarize this with just kind of a curve and say this histogram can be represented with a curve like this. And we would say this histogram is unimodal and symmetric. Unimodal means one peak, and symmetric means symmetric. So we've got one peak, and then we have that. So this could be maybe the distribution of female heights. We could ask a whole bunch of people how much they weigh.